In this video, we're going to solve an exercise of rural-urban migration very similar to the one that you have in your homework. Let's start with the assumptions. We have a consumer that consumes bread and housing. But here's the important part. We have an income that it's equal to y in the city, and then we subtract from that the commuting costs. The commuting costs are given by x, the distance, times the cost per mile. Now, suppose that the jobs in the city are fixed at j, and y will be the income in the urban setting, and ya will be the agricultural income. Now, suppose this is an island and the island has 10 blocks. It can expand later on, but right now, think about it very simple. Now, the employment center will be on one end, and the city will spread along the length of the island to accommodate the population. So the edge, the farthest house, will be X bar blocks from the employment center. Now, assume that each consumer, each citizen, consumes 0.001 square of block of land. Okay, now we need to compute, first of all, the land area of the city in terms of X bar. So basically what I just draw here, it's the image of the island. We have the edge located X bar blocks from the employment center. Okay, compute the city's land area in square blocks. As a function of X bar, the land area is 10 times X bar. Okay, now assume each resident consumes 0.001 square block of land. Now, what is the amount of land that we need for a population size L? So we will need 0.001 times the population, of course, knowing that each person consumes this much land. Now, the next question says, now set B equal to A, because this is the land area, and this is how much every person, the total population needs in terms of land. And now we can solve how much is X bar in terms of the population. In other words, if the population increases or decreases, how much will X bar change? Where X bar, as you know, is the distance from the center to the farthest house. We equate the land area to the land needed, and we get that X bar is equal to 0.0001 L. So this is the equation that gives you how much land you need in terms of the population. It's a little counterintuitive that the textbook uses L for population, but well, bear with me, L is population. Question number 2 will ask you, with J jobs in the city, the chance of a resident getting one of the jobs is J divided by L, which makes the expected income of a city resident equal to Y times J divided by L. The expected disposable income net of a commuting cost for a resident living at the city's boundary will be Y times J divided by L minus the commuting cost, which is T times X bar. The rural-urban migration equilibrium will be achieved when this disposable income equals rural income. So write down this equation and substitute your solution in terms of X bar in terms of L. So first of all, substitute your solution, the one that we got in question 1, where we have the distance in terms of the population in the equilibrium condition. Just to make sure this is the equilibrium condition. The income from the agriculture must be equal to the income from the city minus the commuting cost, because we are assuming that in the agricultural sector, people don't need to commute. They just turn around and there you have the corn, the farm, and you don't need to commute. However, in the city, there's commuting, so we have the income from the city minus the commuting cost. And since we don't have certainty in having a job, we need to multiply times the probability of having this job. So this equation needs to be equated to the agricultural income. And if we substitute x bar with this equation, 0.0001L, then basically, well, we just have this new equation. B. Okay, now multiply the term by L and get a quadratic equation that determines L. As you can tell, what they want us to do is to obtain the population in equilibrium and what determines that the population changes or not. Now we multiply the term by L and get a quadratic equation. So this will be y agriculture in this side of the equation will be negative times L plus y times j. This L divided by L will be equal to 1, so you don't need to write it anymore, minus t times 0.0001 L squared. This is equal to 0. And this is a quadratic equation that when you solve it, you can know what is the value of L. Now, question 3 will give us some assumptions. Let's suppose that the income in the city is $10,000. Let's suppose that the income in the agricultural sector is $2,000. Assume that the cost per mile, per block, of commuting is $100. And let's suppose that there are 30,000 jobs in the city. Now, let's use the result from question 2 to solve for the equilibrium population. So we have here our equation, and now we're going to substitute the numbers that we already know. So instead of the income from agriculture, we're going to have the 2,000. Instead of the income from the city, we're going to write 10,000. The 30,000 urban jobs minus 100 times 0.0001 L squared. We simplify it a bit and we get this number. And now what we want to do is to simplify it as much as we can to solve for L. So we're going to factor out this number. You can factor it out like 0.01 or as 1 divided by 100 because it's the same thing. So if I take this number outside of the parentheses, inside the parentheses, I would be left with 2,000 times 100L plus 3 million times 100 minus L squared. And now this term becomes 200,000 and this term becomes 30 trillion. And we have this L right here. Now, when we solve for L, we need to find two numbers that multiplied will give us this number and added will give us this number. That's one way of solving a quadratic equation, and we can use that method in this case. So if you recall, this is the quadratic equation, and this would be the formula to get it without factoring out. But let's do the factoring because it's easier in this particular case. I just wrote everything again so you don't get lost. We have this quadratic equation. We can simplify it with 1 divided by 100. We put this outside of the parentheses, which is called factoring. And now I need two numbers. One will be minus L and the other one will be plus L. So now I only verify for you. If we multiply 100 times 300,000, we'll get this 30 trillion that we have originally. And then we multiply the same term times the second element in these parentheses, and we get 100,000 L. Now we go to the second term. The second term in these parentheses will be multiplied by the first term in the other side, and we get minus 300,000 L. That would be the proper way to write it. And then we multiply this L times this L, which is minus L squared. And as you can see, we have in here exactly the same as in here. This means that to solve this equation, in other words, for this to be equal to 0, it has to be the case that L is equal to 100,000 or L can be equal to minus 300,000. Since we're talking about the population, it cannot be the case that L is a negative number, so it has to be the solution. Okay, I think I wrote that here. Yeah, so we have two possibilities. Either L is 100,000 or L is minus 300,000. So now the equilibrium population is 100,000 people. This is how many people we have in this city given these conditions. Given that Y is equal to 10,000, the agricultural income is 2,000, the commuting cost is 100, and the number of jobs in the city is 30,000.